So today we're going to be talking about Section 3.5, Analyzing Arguments with Euler Diagrams. Make a note, his name is pronounced Euler, not Euler, but Euler. So I want to talk about differences between a Venn diagram and an Euler diagram. A Venn diagram shows all possible combination sets, even empty. So here's a Venn diagram with two categories. Here's a diagram, three categories. But what if I only have a section and one of the sets? Or here, in this case, I have elements in the section, one of the sets, but not the third category. Well, sometimes a diagram can look fairly complicated when an Euler diagram looks a lot cleaner. These pictures show the progression of how we can convert a Venn diagram into an diagram. Basically, we're taking off the part that is empty, leaving us with this, and then move this MP within the circle, and now we have an Euler diagram. Here's some idea. The middle part here, MP, and this for set S, set M, and set P. S and P would have all three, MP would just overlap between these two S. And so if we remove the part that is not included, have this, S and P is a subset of MP. So this gets moved in, and all of this gets moved inside P. Anyway, this is our progression from Venn to Euler. Let's write down some of the characteristics here. Only includes the sets that have elements within it. Sometimes it's a lot less cluttered. Well, an Euler diagram that I've looked at a few times is the reals. Real numbers is this large outer piece. We break into two categories of rational and irrational. Within the rationals, we have the set of integers. Within that, we have the set of whole numbers. Within that, we have the set of natural numbers. I was going to try and duplicate this with a Venn diagram. I would need 1, 2, 3, 4, 5, 6 overlapping circles. That would look very confusing. But the Euler diagram, clean, simple, easy to follow. And we can use Euler diagrams to determine the validity of an argument. But let's first talk about what it means to be a valid or to valid argument. Argument is it's when true premises force the conclusion to also be true. And I'll tell you what that means in a second. If all of your premises are true, and the premises force the conclusion to be true, in other words, you have what's called a tautology, or all true in your truth table, then we would say that that is an argument. With Euler diagrams, there's going to be no ambiguity as their one set is nested within the other sets. Based off of that, we'll be able to see if the argument is valid or invalid. Just a note with the truth tables, if you have false, then the argument is valid. So start using Euler diagram to determine validity. We're going to use truth tables to verify what we think. So here's my argument. If Jim works hard, he will earn an A. Jim works hard. We're going to read this line as therefore, he earns an A. So looking for my P's and Q's. Working hard, we're going to call that P. I have an if-then statement. If Jim works hard, then he will earn an A. We're going to call it Q. Jim works hard. That's going to be conclusion. He earns an A. That would be Q. Now, if I wanted to make a diagram here, what I have are the set of people that earn A's. If Jim works hard, working hard implies getting an A. So within the A's, we also have a set of people who work hard. And then the question is, where does I have the statement that people who work hard get A's. Jim works hard. That within the work hard circle, which also in the people who get circle. So I would say that this argument is valid based on my Euler diagram. Now, if I wanted to verify that with the truth table, I would have to translate the compound statement. I have P implies Q. This is my first statement. And my second premise. And then together, my first premise and my second premise lead to this conclusion Q. Ooh, with her an E, I don't know how to spell. CS premise. I think better. No, I have no idea. I'm such a bad speller. Okay. So these are my two premises. And then this is my conclusion. And so, premise 1, premise 2 leads to the final thing, Q. And we go to our truth table. I have P, I have Q, I have P, I have Q, and P implies Q. So we're going to just work through this really quickly. False, false. So get the truth table to verify. I'm saying based off the, yeah, this is a valid argument. People who work hard earn A's. So the work hard set is not the people who get A's set. Jim works hard inside this circle, which is also inside that circle. Therefore, Jim doesn't belong to the people who get A's group. True, false, true. So, order of operations inside P implies Q. Remember that For the conditional statement, I only get a false if my antecedent is true and my consequent is false. My false is going to show up. Whoa, that's my baby. My screen's timing out. Sorry. Just give it, huh? Aw, man. Bear with me. Sorry. Technological difficulties. Okay. Okay, we're back. Yes. Okay. P implies Q is only false when it is true and my consequent is false. So here's the false. I know for an and, the and is only true when both are true. So the rest is true, true, true. P is true, false, false. My and is true when both are true, so this is true, otherwise it's false, false, false. I'm going to cross out, I'm not looking at it, cross that out, I'm not lit. Q is true, false, false, and for a conditional statement, only when I have a true antecedent and a false consequent. And the only true antecedent I have is here, which is a consequent, which means this true, 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 true. And this is what we call a tautology. The result of my truth table yield all truths. Therefore, this is a valid argument. Okay, let's do another one. Some dinosaurs were plant eaters. Vegetarians are plant eaters. Therefore, vegetarian dinosaurs. Now, some dinosaurs were eaters. I have this set plant eaters. Within I have some dinosaurs. In fact, what this does is that some dinosaurs are eaters, maybe some. Now, I know that vegetarians are plant eaters. So inside the plant eater, I have you're a plant eater and a dinosaur, or you're a plant eater and not a dinosaur. Based on this, I don't really know where to put my vegetarians. Of course, I know vegetarians aren't dinosaurs. Yeah, I know that. In terms of a logical argument, though, I can't say that my vegetarians go here or here. It's not clear. Well, what if I get the language? Let's cross out some, and let's write all. If I say that all dinosaurs were plant eaters, vegetarians are plant eaters, does that fix our problem? Well, let's look at it with the Euler diagram. Just change what I have here. All dinosaurs are plant eaters. Have those eaters. In that, I'm going to put the set of dinosaurs. I know vegetarians are plant eaters. So vegetarians belong inside the plant circle, but are they here or are they here? Because it's not perfectly clear, I would say that this is invalid. So we're going to, if we're going to verify this with the truth table, we're going to say that dinosaurs are plants. Vegetarians are plant eaters. So this thing's in a third. This is going to be R. Plant eaters we've already assigned to Q. So if you're a dinosaur, then you're a plant eater. If you're a vegetarian, then you're a plant eater. Therefore, vegetarians, which is R, if you're a vegetarian, then you're a dinosaur, which we're calling P. I have my premises. This is my conclusion. It would be premise 1 implies and premise 2 R implies Q. Together, my two premises bring me to the conclusion R implies P. I can do this with the truth table. I have P's, Q's, and R's. And I have P implies Q and R, whoops, went capital. R implies Q. Together, it says that R implies P. Otherwise, it's only a valid statement if we get a tautology. So let's list this out. I have 8 possible outcomes because I have 3 statements. 2 is 8. That's true, 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 false, 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 false. Now I'm going to look at implies Q. I only get my false when the antecedent is true and the consequent is false. So that's what I'm looking for here. Again, I get my false when the antecedent is true and consequent is. So what I'm going to do, just for our purposes, is I'm going to just cover up what I'm not looking at. So I'm going to cover up R. First one. Okay. P and Q, I'm looking for a true implies true implies true, true implies. Okay, so here's a false. Here's a false. Everything else is. Now I'm going to look at R implies Q. R is my antecedent. Q is my consequent. For true implies false, because that'll tell me where my falses go. True, true. Here's a true implies false, so I have a false. And I have another false here. The rest of this column are truths, of this column are truths. My and happens when both true. So I can fill the rest in. The and happens when both are true. So it would be true, true, false, false, true, true, false, true. I'm going to cross this out because I don't need it anymore. I'm going to out because I don't. Now I'm going to do this with implies P. R is consequent. I have. Here's a false, and here's a false. The rest are all true. For my conditional statement, this is where my final answer is going to live. For my conditional statement, I'm looking for a true and false, because that'll tell me where my false is. I have true implies true, true implies true, true implies false, true implies true, true implies true, the rest are all true. This is my final answer for the result of my truth table. And because of this fault here, which I'm going to write in pink so it stands out a little bit more, because of that fault there, my argument is invalid. Now, we knew that it was invalid from the Euler diagram because I where to put my vegetarians. It wasn't clear. I know my vegetarians are plant eaters, but are they inside the dinosaurs or outside the dinosaurs? No, invalid. I tried it with the table. I got a false. Valid. Let's at this last example. All teachers are smart. I read that as if you teacher P, then you're smart. All smart people are rich. Smart, we have Q implies rich is R. That sure doesn't look very good, does it? All teachers are rich. Teachers are P. We're going to call R R. And my two premises, we're saying that P implies Q is my first premise, and Q implied R is my second premise. Implies this conclusion that P implies R. Let's go to our Euler diagram. All teachers are smart. I have more people. All teachers are smart, so teachers into the smart category. All smart people are rich. So all of my smart people fit in the rich category. So the biggest circle I have here is my rich circle. Smart people are rich. So if you're smart, you live inside the rich. All teachers are smart, so teachers belong to the smart category. The set of teachers fits within the set of people who fit within the set of people. Therefore, can I conclude that teachers are rich? Are my set rich people? Yeah, they are. Right. That this is a valid argument. It does not mean that it's true. It means a logically valid argument. Although I can confirm that not all teachers are rich. That is just not the case. Although I would like to think we are all smart. Who knows? Alright. That's going to do it for today. So, thank you. A wonderful day. And we'll see you next time.